Hey all, this is Alan with Bothell STEM Coach, and today we're doing some more AP Physics 1 problem free response questions. We're going to be starting the electrostatic section. Now, one of the challenges with free response questions for electrostatics is they come from the AP Physics B exam, which actually required you to know more things like potential difference and magnetism and all these other concepts that you don't need to know for AP Physics 1. So in this problem, you definitely don't need to know part C. And even part A, I have to give you the piece of information. What I will say is that the energy in part A, that the energy that the particle ought to have as it leaves the tube is equal to Q times the voltage. In this case, that's Q times V naught. In terms of V naught, D, Y naught, and fundamental constants. I think that is all. So let's leave it at that, and then try to do as much as you can in the problem, and then we will. Yeah. So I'll pause the video, try to do the problem from that point on, and then we'll look at the rest of the problems when you come back after you've tried the problem. So part A is calculate the speed of the electrons as they exit the tube. Well, this potential difference, which is basically a battery, imparted this much energy onto the electron. This QV naught that I told you. The amount of energy that the kinetic energy of an electron is 1/2 mv squared. So it's the velocity that it exits out with is v is equal to 2q v naught over m square root. And by m, I mean the mass of the electron. Okay. So these are fundamental constants. It's okay to use q, which is the charge of an electron, and the mass of an electron. Those are constants. Okay. So that's what we'll start with. That's the velocity it comes out with. B, calculate the magnitude of the electric field required to cause the electrons to land at distance y naught and indicate the direction of the electric field. Okay, so this is almost a kinematics, because at this point what this particle needs to feel is a force. And when I have, let's see, this is a uniform electric field. So there's a uniform electric field in here. I haven't said about the direction. So an electric field, so that means the force from the electric field is going to be Q times the electric field. Okay, this is what I need to set up. So I'm under a constant force here, and this is just basically just like an object in gravity, for example. I use kinematics to describe this motion, right? So if I want it to land a y naught away from this point, this distance, I need to look at its initial horizontal and vertical velocities. Well, its initial velocity is horizontal because it was projected out this way. And then so I'm going to need to do kinematics in the x and the y direction. In the x direction, the distance y naught is just equal to its velocity in the x direction times t. And the electric field is vertical, so it's not going to cause this thing to change in velocity. So its velocity is the same the whole time, which is 2q v naught over mass of the electron times t. Okay, just replaced v with vx here, because when I initially entered this region, I have the same velocity. Okay, in the y direction, it also, I'm going to use this equation, delta x equals v naught t plus 1/2 at squared. So delta x, in this case in the y direction, it's going to fall y naught. It has no initial vertical velocity in the y direction. Now, the A is an interesting part. Like I can't solve for t until I know A. And that's where we go to the fact that the force that he's feeling is Q times the electric field. That's equal to MA, right? because F equals ma, right? Like the only, like if I draw a free body diagram on this thing, we're gonna assume that gravity is negligible because it usually would be in for such a small particle. This is a relation. So I know that A is equal to Q electric field over M, and I can plug that into this equation. So I have Y naught is equal to 1/2 Q times the electric field over M times T squared. Okay, so if I want to solve for T, actually I'm trying to think of what the simplest way to, because I don't want to do it. So if I want to solve for T, T would equal, I'm going to multiply by 2 times M divided by QE square root, right? And then I plug that into here. So I get Y naught is equal to square root of 2Q V naught over mass of the electron times 2 this should be ME, mass of the electron, over Q times the electric field. Okay, and then I can combine these things into the same square root, because that's one of the rules of square roots. And then like things will cancel. Mass of the electron will cancel. The charge of the electron will cancel. So I get 2 V naught over E. And now I can solve for the electric field. Y naught squared is equal to 2 V naught over E. And so E would equal 2 V naught over Y naught squared. Okay? So that's the magnitude of the electric field. Now the direction of the electric field, because the force is going down, and this is an electron, it's a negatively charged particle, it always moves opposite the direction of the electric field. So if I want the force to be down, I need the electric field to go up. Okay? When the electric field's up, positive charges move in the direction of the electric field. Electrons move against the direction of the electric field. That's just how we've defined electric field direction. So it's toward the top of the page. Okay? And that's it. Hope you found that helpful. I'll see you in the next video. Thanks for watching the video, guys. Please leave a comment, like, or subscribe below to catch up more of the content. And see any links below. I offer free homework help on Twitch and Discord. See you guys in the next video.